Welcome. One possible view of the world is that it looks like a pyramid. At the top of the pyramid is the P versus NP problem. And at the bottom of the pyramid, there are many extremely important but somewhat specialized problems that one needs to solve slowly and patiently in order to climb the pyramid and get to the top. These problems range from circuit complexity to communication complexity to matrix rigidity to problems concerning polynomials. Now, I want to propose a different view in which the pyramid is upside down. And rather than there being many problems that lead to P versus NP, there is only a few problems, and actually these problems get fewer and fewer while we reach the tip of the pyramid, which is now at the bottom. And a good question is, which problem is right here? What is a problem which is really fundamental and stands in the way of progress to much of the rest of the pyramid? What can we put there? So let us consider various problems that have been studied in order to make progress on P versus NP. One problem is that of proving circuit lower bounds. And for this talk, you can think of proving, say, quasi-polynomial circuit lower bounds, even for depth 3 circuits. I'm not going to be precise on every problem, but some of them will be defined formally soon. Another problem is Valiant's challenge of constructing rigid matrices. These are just matrices which have, say, constant Hamming distance from matrices which have low rank. Another outstanding problem is proving correlation bounds for polynomials, meaning exhibiting functions which cannot be computed well on average by low-degree polynomials. Yet another challenge is that concerning multi-party communication complexity, specifically in the number on forehead model. Okay, and here a long-standing challenge is to proving lower bounds, even worst case lower bounds, when the number of parties is more than logarithmic. Now, of these problems, is there one which is more fundamental than the other, in the sense that progress on the problem stands in the way of progress for the other problems as well? Well, let's see some connections. First, if you want to make progress on circuit lower bounds, except for some quite narrow settings of parameters, you're going to have to make progress on correlation bounds for polynomials. So I put an arrow here from A to B if making progress on A requires making progress on B. Okay, and this arrow is not hard to prove, say by min-max. What about matrix rigidity? Well, it may be a little bit less well known that if you want to make progress on matrix rigidity, then you also have to make progress on correlation bounds for polynomials. What about multi-party communication complexity? Well, it may be even less well known that even this requires progress on correlation bounds for polynomials. Okay? And you can find references and proofs of all these things in my papers. So what do we do in this work? In this work, we put one more arrow. Okay, we consider some recently made Fourier conjectures, and we show that even these recent Fourier conjectures would require first making progress on correlation bounds for polynomials. So based on all of this, I want to propose this specific view in which the pyramid is upside down, and the problem which is at the tip of the pyramid, which touches the ground, is that of proving correlation bounds for low-degree polynomials. Let me now be specific and define this problem. So the challenge of correlation bounds is to find an explicit function f from n bits to 1 bit and some distribution x such that for every polynomial p of degree d, the correlation between f and p is small. And the correlation here is justified as the probability over an input drawn from x that f of x is equal to p of x. And small means at most half plus epsilon. Note that you can always find the polynomial p which agrees with f with probability at least half just because f is Boolean, and here we are saying you cannot do much better than that, you can only do at most half plus epsilon. Back in the 80s, Rasborough and Smolensky showed that for the function majority and for the uniform distribution x, you can prove a bound that epsilon is at most order of d over square root n. Okay, that is, under the uniform distribution, every polynomial of degree d, okay, agrees with the majority function on at most an half plus order of d over root n fraction of the inputs. Okay, so this bound on epsilon is vanishing as long as d is less than root n. So it can handle fairly large degrees, but the bound on epsilon is only at best 1 over root n, and obtaining a smaller epsilon, proving a smaller bound on epsilon for any explicit function remains open for any degree which is larger than log n. Okay, for tiny degrees you can do something different, iterated Cauchy-Schwarz, but for degrees larger than log n, this bound remains the best known. And improving this bound stands in the way of progress for each problem on the previous slide. So what about these Fourier conjectures? So recently, a new paradigm has been developed for constructing pseudo-random generators. This paradigm is called polarizing random walks, and it can construct pseudo-random generators from Fourier bounds, from bounds on the Fourier spectrum of functions. So a specific goal of this paradigm is to obtain better pseudo-random generators for low-degree polynomials. The state of the art about generators for low-degree polynomials has not changed since the works from more than 10 years ago, and is limited to polynomials of degree at most log n. So in an effort to obtain generators for polynomials of degree even larger than log n, with this paradigm, several Fourier conjectures have been proposed, have been made. So one conjecture is that the sum of the Fourier coefficients of size 2 of any polynomial of degree d should be at most order of d square. And another conjecture is that if you sum the Fourier coefficients of a degree d polynomial of size k, then you obtain 2 raised to little law of decay. It has been shown in these works that if you can prove these things for low-degree polynomials, then you would indeed have new pseudorandom generators that improve on the state of the art using the polarizing random walks paradigm. So in this work, we show that these conjectures, and in fact even weaker conjectures, would imply correlation bounds which already beat the Rasborough-Smolensky bounds. Okay, so proving these conjectures on the Fourier spectrum implies better correlation bounds that we have. And these correlation bounds, which are implied by our connections, are for functions which are related to majority. So for example, the function which, given input of n bits, takes the sum of the product of every pair of bits and checks if this sum is at least half. And if I think of the bits as being +1 and -1, I can just write bigger than 0. This is the function that you get from the first conjecture here. If you look at this other conjecture here, where you sum the coefficients of size k, you will get the function in which you take products of size k. Motivated by this conjecture, motivated by this connection, in this work, we also prove several new correlation bounds. These correlation bounds aim to, but don't, resolve the Fourier conjectures. We specifically prove new correlation bounds for the function which was on the previous slide, which is related to majority. However, it seems more natural to just start with majority, and our starting point is the observation that in fact the correlation with majority is still open. So we prove several new results about majority. The first thing that we prove is that Smolensky's bound of epsilon at most order of d over root n for majority is in fact tight under the uniform distribution. Okay? There are polynomials which achieve this correlation under the uniform distribution. So we cannot improve the bounds under the uniform distribution, but we could do so under some other distribution. And in this direction, we exhibit polynomials which achieve omega d square over n correlation, meaning they agree with the function half plus omega d square over n under every distribution. So for every distribution, there is a polynomial which has this correlation. Okay, this bound here is weaker than Smolensky, is quadratic in Smolensky's bound, but on the positive side it holds under every distribution. And we conjecture that this bound is tight. Okay? That there exists a distribution with respect to which you cannot improve this bound, and in the paper we have a specific candidate for what would be a hard distribution. Proving this conjecture seems to be a nice direction to better understand majority, and we are able to prove it in the specific but not completely trivial case of linear polynomials. in which case we also improve Smoleski. Okay, so we show that for linear polynomials of degree 1, the correlation is not order of 1 over square root n, but is in fact order of 1 over n. And even proving this for degree 2 seems interesting. So a suitable extension and strengthening of these results would disprove the Fourier conjectures.